All right.
Morning, everybody. My name is Blake. I'm the project manager on the SolarAirplane team. With me is Bone. This is my avionics lead, and Lupe, she is my mechanical lead. So the goals and objectives. So the goal of this project is very educational. So what we're trying to do is we're trying to provide students the ability or the opportunity to design and manufacture their own UAV. It has to carry a 2-kilogram payload, technical, so it could be a camera, it could be sensors, it can be anything that's recording data. And the whole purpose of that is we need to integrate solar panels into it to extend its flight time. So one of the concerns that we've been brought up was how are we going to test this? Our team resolved to make the plane have removable wings, so you can swap out the wings with solar panels and without solar panels. So the objectives, so we broke it down into 3 main steps. The first is we're going to be developing a UAV. We're going to limit all mechanical losses first, make it fly as efficiently as possible. Then we're going to limit all of the electrical losses, make sure all of the wiring is good, make sure it's all efficient, and that there's no unnecessary components to it, and that it's very easy to manufacture and assemble. And then finally, we're going to be optimizing the power generation. So how we're going to be putting the solar panels together, if there'll be any circuit elements such as power boosters, any kind of things like that, that will make sure that we have all available power to extend the flight time of this UAV. So the background. So this project's been hosted at UCI for 6 years. For half of its lifetime, it was under the material science department, where they were just trying to find out what solar panel combination was the best. Anything that was from that period, I have absolutely no data on. I don't know if they're successful or not. But once it transferred to the mechanical department about 2 years ago, the first plane looked like a plane. It was fully assembled. It looked nice. However, they had constructed their own battery packs, and because of doing this, they actually ended up short-circuiting one, and the plane never flew. So it's actually still in my lab right now. And then last year, the ambition was also pretty high. The problem was they wanted to carbon fiber mold everything. So that process takes a while to actually make the plug and the mold. So by the time we actually got to manufacturing, it was already spring quarter and it was too late. So this year, one of our more personal goals is we're trying to compile as much data as possible from the design, manufacturing, to its performance, all the simulations possible, so that future iterations of the team don't have to go through the approximately 2 years of archive getting very little data. That was one of our biggest challenges, was starting from scratch when most plane projects, especially after this long of a run, already have things to look at and they already know what works. We're still trying to figure out what works, and we're doing pretty well on that. So going forward, next year or years later, we're hoping that we can get this plane to be fully autonomous, to where you set it down and it flies by itself. It will be fully programmed to run a specific path. These are possible using flight controllers. Okay, so I'm going to hand it over to Feng right now. She's going to be talking about the requirements of the project.
So the first requirement is that since fall quarter, we changed our requirement from a maximum UAV weight of 20 pounds to 12 pounds. We have the UAV dimensions to 26 square feet, which is supposed to be 4 by 6 feet, which is the average size of a truck bed. Technical payload of 2 pounds, again, such as a camera or sensors. Minimum flight time of 10 minutes, and that the solar panels must extend the flight time by 15%. So if it was 10 minutes, then the solar panels would extend the flight time by 90 seconds. It must fly at 456 to 700 feet above sea level. It must have 2 control systems that respond to the environment or operating conditions. So for example, the environment would be air conditions, air pressure, and then operating conditions would be such as like if the plane were to get damaged in some way. And then one component must be made of carbon fiber. Right now we're thinking of having some of the electrical mounts being made out of carbon fiber, or maybe the landing gear, but we're still working on it. So the timeline right now is that winter quarter we are working on fabrication. It's going very well. We, for example, we have the complete model of a tail right now. We're in the process of laser cutting all of our balsa wood. working on avionics, testing all the components and the solar panels, and then we will integrate that into our manufactured model. And then spring quarter, we will have our complete model to fly and test and then optimize. So the progress right now, or this is our progress right now, our milestones are testing electricals, manufacturing all of our assemblies, and then fully integrate our airplane.
So more on the progress. So I changed a little bit of the format because originally reviews was red, but you know red should be that you're a little behind. So everything in the reviews is on time except for the integration. So I had expected by this point that we could start a little bit the integration, but because manufacturing, the plan of manufacturing took a little bit of time, we ended up having to halt integration. Hopefully by week 7 or by week 8, the end of it, we'll be ready to start integrating some electronic components. By the end of this week, we should have all of our electrical systems tested and benchmarked. So everything's already been benchmarked. The batteries, all the components, all of our safety equipment. The last thing that's necessary are the solar arrays. Those are being currently soldered together, and we're trying to see how much output they have versus the time of day and things like that. And then by the end of approximately week 9, the last milestone is that we're going to have all of our mechanical components fully built and assembled, waiting to just be put together into one unit. The biggest problem with this and why this is such a milestone is because when it comes to a lot of airplanes, if there was not constant communication, you might have one part that's slightly too big, or one part that doesn't quite fit the dimension. So if we can get it to where it's just ready to basically be tapped together, then that means that communication was great. It means we can move on to optimization and testing, and it means that we can leave that whole fabrication behind and that our fabrication step was effective. And so I'm going to hand it over now to Lupe, who's going to talk about our budget.
Okay, so the budget for SolarAirplane for the winter quarter was about $5,000. So that's money that we got this quarter and what rolled over from last quarter. So our budget is split into 3 main categories: the mechanical, electrical, and manufacturing expenses. So for example, some manufacturing expenses here in yellow are the money that we have to pay to use Rapid-Tech and FabWorks. So that's for laser fitting our whole airplane. Some electrical expenses in red are all the electronics that go inside the airplane. So that's like the pixhawk, the motors, the servos, all the wires that we use to connect all of the electronics together. And our biggest expense is our mechanical expense, so that's everything that goes into building the airplane. So for instance, there's the balsa wood, there's the monocoat, and there's all the tools that we use to put everything together. So this is what we've spent so far out of our $5,000. And as for resources for the group, our advisor is Professor Yun Wang, and we have 31 students in the team. So we have 3 team leads, 1 document manager, and 27 general members. So we have weekly meetings on Mondays from 2 to 3 in the base living room at Engineering Tower, and that's basically just where we delegate our tasks for the following week and review the tasks that we assigned the previous week. And outside of this, we have 5 sub-teams, and then we have 1 lead meeting per week. So each of the sub-teams and leads have their own meetings, and those go on for a variable amount of hours based on what we have to do that week. But generally, it's about 1 to 3 hours. And so community commitment for the week, not including meeting times, it's about 124 hours, including all students' commitments. So this is just a roster of our team so far. Our team grew by about 50% from last quarter, which is why we were able to, we only had those 4 sub-teams before, but now we were able to add a landing gear sub-team because it's also important to the plane, and now we have the amount of people that we need to have our own team for that. So each team has on average about 6 or 7 students. And this is our sub-team structure. So we have the 3 leads and then all of our sub-teams. So as a mechanical lead, I oversee more of the teams that don't really use electronics, so all of our parts are more static. So I oversee the fuselage and the tail team, and I'm part of the fuselage team myself. And Blake oversees the landing gear team, and Feng oversees the aero and electrical teams, so that's the wing and avionics teams. And even though we all have our respective teams, as Blake was saying earlier, there has to be a lot of constant communication within an airplane building team because all of our parts have to be perfectly integrated. Like we can't have a fuselage that doesn't fit all the electronics in it, and we can't have wings that are not like the right ratios for the tail. So it just takes a lot of constant communication for our team to be successful. You don't have any questions or comments?